You are difficult to teach because you have already entered a situation where you are doing your own thing. The film itself and its sale are somewhat limited, meaning there is a small range in what you are working with, and that is what gives you your own thing. In a way, contrast affects the range of exposure. If you increase or decrease it, you experience a circumstance of underexposure or overexposure. If you increase it, you enter underexposure, and if you decrease it, you also enter underexposure. In digital radiography, you have a slightly larger range of exposure. In the context of digital imaging, when you alter technical parameters, if you increase or decrease them, your machine won't be as sensitive as the screen in the field of radiography. You can adjust if your milliampere value decreases or increases significantly. The idea here is that a simple change can bring about improvements, for instance, the change between these images. What is clear here is that to improve this, if you have the image, for example, you reduce it and it tells you to multiply the milliampere by 2, multiply your milliampere by 2 to return to the previous state. So what is the name of the milliampere divided by 2? This is a rule for you, especially in screen film radiography. There is a rule called the 15% rule. The 15% rule tells you that it establishes a relationship between kilovolt and milliampere. It says that if you want to maintain the dose for the patient, for example, and at the same time, you want to increase the kilovolt, what should you do with the milliampere to maintain that dose while also achieving the image quality you are looking for? It says that if you increase your kilovolt by 15%, then reduce your milliampere to half. If you decrease your kilovolt by 15%, then increase your milliampere to double. This is called the 15% rule, and it is commonly used in radiography because it is crucial for the topics of accuracy and delivery. This rule is important in the field of radiography because it helps ensure that the correct dose is delivered to the patient while maintaining image quality. This is particularly important when considering the balance between image quality and patient safety. The 15% rule is a guideline that radiographers often rely on to make informed decisions. Here, he is essentially saying that these are free images available at different milliampere settings. You are essentially increasing them all above 70 kilovolt. The image number is essentially related to milliampere seconds. If you increase by 25% every time you increase, there will be an increase. In density, this is essentially an example we talked about earlier regarding milliampere. Before we discuss it further, if I am essentially talking about X-ray radiography, this is referred to as milliampere seconds, which is the effective milliampere. For example, if you set 200 milliampere with an exposure time of 0.1 seconds, your effective milliampere is 20 milliampere seconds. If you set it to 400 with 0.1 seconds, then you have 40 milliampere seconds. They prefer to use a shorter time to avoid patient movement, which can lead to motion unsharpness or blurring. If you want to give milliampere, you can essentially reduce it to achieve the same results as using 400 milliampere with 0.1 seconds, resulting in 40 milliampere seconds. Basically, they prefer to use a shorter time to avoid patient movement, which can lead to motion unsharpness or blurring. If you want to give milliampere, you can essentially reduce it to achieve the same results as using 400 milliampere with 0.1 seconds, resulting in 40 milliampere seconds. So you reach the same as here, for example, you are at 40 milliampere seconds with 1 second exposure. When you are operating with a low milliampere setting, it is essential to understand that you will have to incrementally increase the milliampere value multiple times. This adjustment process is necessary to ensure that the effective milliampere level is correctly calibrated to meet the required operational standards. By doing so, you can achieve the desired performance and efficiency in your device or system. It is important to monitor the changes closely and make precise adjustments to avoid any potential issues that could arise from incorrect settings. The same thing. All right, doctors. Is everything okay so far? Good, Yusuf. Thank God. I just want to talk about the topic of optical density. I might have taken some things from screen film radiography. I entered it. But honestly, I found that the topics are quite similar, especially in image quality and such. So, just to clarify, there are important things that we will discuss. Now, regarding the optical density of the X ray film, each film has a sensitivity to radiation called the speed. This film has a certain speed which represents the film's speed or sensitivity to radiation. Now, this film for X rays, if we consider that we all have the film badge that we use because we use it in cases like TLD, for example. When we use the film badge in the past, the film badge is a film that when you move in the radiation center gets exposed to radiation, and this radiation starts to cause blackening on the film. According to the blackening that occurs, it begins to measure something called optical density, which reflects the extent of the blackening or darkness that has occurred in this film. It starts to tell you that if the blackening is very high, this means that this film is very present in radiographies and has a calibration curve that indicates the expected dose for this person. If their exposure is low, it means that this film is more sensitive, for example, indicating that this person has not been significantly exposed to radiation. This was the idea behind the film, and the same concept applies to films that have the H&G curve, which characterizes the film's sensitivity to radiation. So what do? They use something called a sensitometer, which comes from the word sensitivity and measures the sensitivity of this film. So how does this work? Well, I am now possible. Explain it better. I have an X-ray tube and I have the film. This film uses something that consists of blocks like this, but with different thicknesses. Here, the thickness is large, and then it decreases gradually along the range of the film or along the length of my film, and it starts to be exposed to X-rays, right? So, normally, the part that has higher thickness will absorb a lot of radiation, meaning the transmitted photons that reach here, that reach the film itself, will be fewer, right? So, this part is supposed to, it will remain unburned using the existing radiation because a large part of it is absorbed due to the weight of materials like aluminum or the hydrodynamic materials, which absorb a significant portion of the radiation. Therefore, no blackening occurs. The next part absorbs less. So the blackening starts to increase slightly, then less, less, and less. You begin from the white until you reach the dark or black at the end. So you have effectively done something similar to what you did on the film. Then, what does it start to do? It begins to measure, taking the film itself and measuring it, meaning what I am doing now. I have an object in an organ with both transmitted and incident radiation. I will refer to this object as the I node. Let's assume the I node, incident on my object, has 100 photons. If we assume that the translator here is 100, this means there is no correct experience, right? If we say 100 incident and count it as 100, then I see that there is nothing. Is that right? If we say it remains if a transmitted over I node equals 1, correct? Here, for transmitted 100 and incident 1, this is strong. I call this transmittance. The percent of transmittance is calculated by multiplying I by the transmittance. If I have a value of exactly 100 in transmittance, that means precisely 100%. In other words, to calculate the optical density, you take the logarithm of the inverse of the transmittance. Essentially, the inverse of the transmittance means the logarithm of 1 over 1. So, the logarithm of 1, when we come here, is log 1, which equals 0. In mathematical terms, a logarithm is the power to which a number must be raised in order to get some other number. This means that the optical density of this part is 0, which is good. Optical density is a measure of how much a material can prevent the passage of light through it. In this context, having an optical density of 0 indicates that the material is completely transparent, allowing all light to pass through without any obstruction, which is beneficial for our purposes. Well, this is what basically happens in the film. I see that the entire film essentially has degrees, with a white part here, and then it actually increases in degrees until it reaches black, right? So, I have the film looking like this here. Indeed. At some point in time, when it reaches the black, it starts using a specialized device known as a densitometer. Note carefully that there is something called a sensitometer, which is specifically used for the purpose of the calibration curve. As for the process of calculating optical density, that's done with the densitometer I use. When I previously mentioned, I take the film and see how much it burned in terms of both burning and darkening, the exact same story applies here. I take this particular device, the densitometer, which is equipped with a source of radiation as well as a detector, and I meticulously check how much incident light there is and how much has successfully passed through. The part that is completely white, which is ideally supposed to have 100% transmittance, or perhaps less, means that the white part, which hasn't burned on the film, will show a question mark. As for the part that is the bride, the transmittance that will pass through it is due to the fact that it hasn't burned at all, so it should be normal. The transmittance here, or the IT here, we will assume it is at 100%. If I have 100 photons falling, what is the transmittance? If we say 100 over 100, it will be 1. So when you calculate the value of the optical density for the part that is the bride, you will find it is 0. Great. If we say that in the case where I have 100% transmittance, my optical density was 0. Now, if I reduce this transmittance by 50%, what does 50% mean? What does 80-50 exactly signify? And if the I0 was precisely 100, what is 80 over I0? It became 0.5, which is 1 over 2. Now the optical density logarithm, the reverse of transmittance means 1 over 2, which gives you 2. Let's find out what the value is using the calculator. 2 log 0.3. So, when the transmittance decreased by 50%, how much did the optical density change? It went from 0 to 0.3. Let's say I want to reduce my transmittance to half of what it was. I had 100,
the optical density was 0, and with 50% transmittance, it became 0.3. Let's say I make it 25%. So the transmittance is 0.25. This means that the incident mid-photon transmittance is 25, which is 0.25. So 0.25 is my transmittance. My transmittance value is 25, which is 25% when you multiply it by 100. The optical density will be the logarithm of the inverse of 0.25, which is approximately the logarithm of 4, resulting in 0.6. Therefore, I noticed that the optical density here decreased when I reduced my exposure. What you mean by 100% is essentially saying that your exposure has decreased from 100 to 50 because the number of photons has decreased. The change that will occur in optical density from 0 to 0.3 and from 0.3 to 0.6 and so on means that reducing the exposure to half will cause a change or an increase in your optical density by about 0.3 each time. That's what happens. After measuring the values of optical density here for your entire film, it establishes a relationship between optical density and exposure, which is such that the values I mentioned, specifically the narrow exposure latitude, are better observed in images, making the picture look better. This relationship is crucial in the field of photography and imaging technology, as it helps in understanding how different levels of exposure affect the final image quality. By analyzing these values, photographers and imaging specialists can make informed decisions to enhance the visual appeal of their work. And this is the different approvals. 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 The sensitometric curve plots optical density. From exposure ranges to form steep wage density. The logarithm of relative exposure indicates a change by a factor of 2. It comes from the range of exposures that are used to create the staples for dentists. These are the staples for dentists. The logarithm represents relative exposure, indicating that changing the exposure by a factor of 2. The change in exposure by a factor of 2, what I told you is that you either double it, increase it, or decrease it. So the change you have is by the amount we were talking about. Now come here. The O3 represents a change in social change. A change in the logarithm means that an increase of 0.3 in log relative exposure doubles the amount of radiation exposure, whereas a decrease of 0.3 in logarithm relative exposure refers to the reduction in relative exposure that we were discussing. Thus, exposure increases the optical density. Whereas a decrease in logarithm relative exposure means the cut in the relative exposure that we were talking about. It's like you're reducing the amount of radiation exposure as if you're dividing it by 2. On the other hand, increasing it is like multiplying it by 2. This is the curve that emerges, and from this curve, you can start to determine the sensitivity of the film itself. At a certain area of this region, it is referred to as the base, where you check its value. For example, it might come out to be 0.18. You add 1 to it and start taking this projection to see this point, which is called the spit point. The spit point is where you check where this point is on the exposure, at what value in the radiation exposure. If you compare two films, for example, film A and film B, you will find that the first point in film A has a high effect of 1.5, while the second point in film B has a high effect of about 2. This difference indicates that at the same point, having a high effect will reach the same value of optical density. This means that film A, what does that imply about film A? Speed or faster speed means having more than one film. If you can see the film's characteristics through creating this curve, you can start comparing. You will find that as you move towards a certain direction, the film's response changes. To attract attention, you remain highly sensitive and highly fast. The word speed indicates that you are closer to the y-axis. In this case, you are more sensitive to the response. The lower the speed exposure point, the faster the film speed, meaning that the sensitivity increases. When the exposure point on the x-axis is close to 0, you achieve optical density with a lower dose. In this case, a lower dose allows you to reach your optical density for image quality. Conversely, the higher speed exposure point corresponds to slower film speed, which reduces sensitive degradation. For example, in film B, I need a dose of 2 to reach the same value of optical density, while 1.5 in film A was sufficient to achieve the same optical density. Thus, film A has a higher speed than film B and is more sensitive. The slope, referred to as gamma, is steeper when the curve is more straight, indicating high gamma. What does this mean? For example, you came to look at 2 points of exposure, such as this specific point and that particular point over there. For instance, this point could be related to financial exposure, and this point might pertain to environmental exposure. Understanding these points is crucial because they help in assessing potential risks and impacts. Exposure, in this context, refers to the degree to which a system or entity is open to potential harm or loss. By examining these points, you gain insights into vulnerabilities and can develop strategies to mitigate them effectively. This is a very small comparison. The same comparison is the same. However, the distinction lies in the fact that there are 2, 2, 2, and yet another 2, making it a total of 4 2s. The film's effect on the values of relative exposure or your exposure allows you to achieve a high difference in optical density, while here, the small exposure gives you a small difference in optical density. This is related to what they call high gamma film or low gamma film. So the film here affects the contrast of the image. Of course, it has an effect on the contrast of the image, especially when we talk about screen film radiography. High gamma, low gamma, shallow slope, low contrast. Be aware that, for example, you will find the part I was telling you about, which is your narrow exposure or narrow exposure latitude. In screen film, they cannot create a large range of exposure that gives you the same contrast you want. They cannot do this. This is one of the drawbacks of screen film radiography. I cannot create a wide range of exposure as a characteristic of the film itself. Therefore, the issues of screen film radiography regarding underexposure or overexposure were the most common. All right, let's go back. Radiography film was in the subject of the was. It is you will always find that the topic of optical density in some devices ranges from 0.2 to 3, and in some devices from 0.2 to 4. This is the topic they call exposure density. I want to show you an image of the dense 2 meter, which measures optical density. The density meter measures optical density because, as we said, you have a light source that emits light, and it starts by placing the film here. it begins to observe the transmitted light and then uses the equation I mentioned earlier to calculate its optical density